So that's why here we have the standard normal, and this is the dicupola with a constant, the blue one. Okay, so that is the distribution we use when the cointegration vector is known. We don't have to estimate it. And then after that, if you estimate one parameter, it shifts to the left. And the more parameters, the more independent variables you add, the more it shifts to the left. Okay, then last time we also looked at this consumption function, right, where consumption is a function of income and wealth. So we estimated so looking at the relationship between consumption, the blue line, income, the red line, and wealth. And so we did a regression of consumption on these two variables, and this was the residual. And now we want to test whether this residual is stationary. Okay? And that if it is stationary, it means that consumption is co-integrated with income and wealth. Okay? So So from the regression, we get these estimates of the beta, and then we use that to construct the residual. Okay? And once you have the residual, you do the ADF test to test for cointegration. And here we look at the t-test, and our t-test for a constant minus 3.27. Okay? Now, what is the relevant critical value that we will compare it to? What is the correct critical value that we should use from this table? It should be should it be? Minus 3.74, right? Because we have two I1 variables, income and wealth, so two estimated parameters, so this is the relevant critical value. So we will compare minus 3.27 with minus 3.74, and can we reject unit root? Cannot reject it. Right? We cannot reject the null of a unit root in the residual, so that means we cannot reject the null of no co-integration. So we cannot reject a unit root in the residual. That means consumption is not co-integrated with income and wealth. Okay? So that tells us that this model, the consumption function that we are trying to estimate, is missing something important. Right? Just income and wealth cannot explain consumption. Something major is missing, and we need to add that variable in order to obtain a stable consumption function. Okay? What that variable is, maybe theory can be a guide, could be interest rate, could be some other business cycle variable, and so on. So what this exercise tells us is that something is missing. You need to add something to your model. Okay, now there's some other ways of testing for no co-integration using the error correction model, but I'm going to skip this. So you can cross this out. Okay, so now what I want to do is I want to show you how to implement these tests in eViews. And also, we are using a single equation approach. And one important assumption of the single equation approach is that there is only one co-integration vector. There is a unique co-integration vector, okay? But in the real world, there could be multiple co-integration vectors. So when we are testing, we should be aware of this limitation of the single equation approach. And I will show you a method which also allows to test for multiple co-integration vectors. Okay, so we're going to eViews now to see how we can do this testing. So if you have brought your notebooks, you can open eViews. I have uploaded a file called US Money Demand. So please, if you have eViews, then you can download and open this file in eViews. Okay, so this file has a few variables, and you're going to use this file to estimate money demand in the US, whether there is a stable money demand function. Today I'm going to show you, last time we talked about the term structure of interest rates. And the term structure theory tells us that the long-term interest rate is a weighted average of the short-term interest rates that are expected to prevail over the life of the long-term bond. Okay? So one implication of the term structure theory is that the short-term interest rate should be co-integrated with the long-term interest rate. So we can test that over here. So in this file, maybe too small for you to read from here, there is a long-term interest rate called USINT 10. That's the 10-year US interest rate. And there is a short-term interest rate called USTB3M. That's the 3-month Treasury bill rate. Okay? So we want to see if these variables are co-integrated with each other. So I'm going to select these two. Open the group. We can first view a graph. Okay, so this blue line is the 10-year interest rate on the 10-year bond. That's the long-term interest rate. And the red line is the 3 months Treasury bill interest rate. That is the short-term interest rate. So if you just look at a picture, then do they look co-integrated? Yes. Okay. So does look. First of all, they are very volatile. You can see going up dramatically and coming down dramatically. Last few years, 2008, 2009, you can see the financial crisis made the short-term interest rates close to zero. That's the well-known liquidity trap, right? Nominal interest rates close to zero. So we want to see, is there any long-term relationship between these two variables? So what is the first thing in our analysis? Before we test for co-integration, what should we do? So you've seen a plot of the variables. What should be the next step? Unit root test. Okay. First, we have to check, do they even have a unit root? If there's no unit root, then we can use the standard OLS type of thing. Okay. But if there is a unit root, then we have to test for co-integration. So first thing should always be to check for a unit root. So let's just open the long-term interest rate and then do a unit root test. In the level, should I include an intercept? Should I include a trend in the equation? No. Okay, so nominal interest rate hopefully should not have a trend in it. So just a constant, and let's just stick to automatic selection. Okay, so that's a unit root test. So what can we conclude from this unit root test? Reject. Do not reject. Okay? Null hypothesis of a unit root, and null hypothesis is that there is a unit root, and you can see we cannot reject the null of a unit root. This is the t statistic, and this is the critical value. It's a little bit out of alignment, but this is the p-value. So we are unable to reject the null of a unit root. That means the long-term interest rate has a unit root. Okay? Do the same thing for the short-term interest rate. Okay? I'm not going to do it. You can try that. So now let us open both of them together. Click on View, and you come to co-integration test. Okay, so when you come to the co-integration test, you see that there are two options here. One is a single equation co-integration test. The other is Johansson system co-integration test. So first we are going to look at the single equation co-integration test. Okay, and here, test method. There are two choices here. First is Engel-Granger, and the second is Phillips-Uliaris. So there are two single equation methods. We are going to do both of them. Okay. So first we use the Engel-Granger method. Okay, so here, specification of the equation, what should we include? Constant we also have choice of a linear trend or a quadratic trend. So no constant, we're going to have constant, linear trend, quadratic trend. What should we pick? Linear trend. So you think that the long-term and short-term rates have a linear time trend? Yes? Well, if they have a linear time trend, if it is positive, that means they're going to keep on increasing forever. If it's negative, decreasing forever. Unlikely, right? So I wouldn't want to include a trend. So I would just, if you, so if you just look at a picture, you just saw the picture, right? So here, now it's confusing, right? Should you include a linear trend or not? Okay, so based on this picture, well, in the first half, looks like there was a trend going up, in the second half, going down. But there isn't a single trend, right? If it was like this, then you can include a trend. And if it's like this all the way, you can include a trend. But here, we don't really have a trend. And then the other thing is we also have to think about economic theory. Okay? Is it possible that the nominal interest rate has a positive or negative time trend? Right? That seems unlikely. So let's go back to the single equation cointegration test. Okay, so we just leave it at constant. Don't include a linear trend. Lag specification, let's just use the default Schwartz information criteria for the number of lags, and you press OK. And these are the results. Okay, so let's look at these results. Okay, so these are the two series that we are looking at, the long-term rate, the 10-year rate, and the 3-month rate. Null hypothesis, they are not co-integrated, okay? And we are including a constant. Automatic lags, we are choosing based on the Schwartz criteria. Okay, now the results. Now, they give you results in two ways. One is, this is the long term is the dependent variable, and the short term is independent. The second is, the short term is the dependent variable. Okay, so both ways. So this is the ADF tau statistic. This is the p-value. Okay, and this is the case. This is the p-value when you use the other way around. So what is the conclusion from here? We can reject the null hypothesis, right? So p-value is smaller than 5%. That means at the 5% critical level, we can reject the null hypothesis that the series are not co-integrated. That means the series are co-integrated. So short-term, long-term rates are co-integrated with each other. Okay, so this is the Engel-Granger test, okay, which is basically applying the ADF test. So it's a two-step procedure. In the first step, you do an OLS so that you get the co-integration vector. In the second step, with the co-integration vector, you construct the residual and you apply an ADF test to the residual. Okay? And so that's what this Engel-Granger test is doing. Now, another, so for single equation methods, we have two tests. We have Engel-Granger, and the other one is called Phillips-Ulliaris test. Okay? Again, we're going to keep the same specification constant and click OK. So now, so this is the Phillips-Ulliaris test, and once again you see that we can reject the null hypothesis of no co-integration. So that tells us that there is co-integration. Okay, so these are two single equation methods. Now the third method that I'm going to show you will be the Johansson method. So go back to co-integration test and click on Johansson system co-integration test. Okay. Now this is a bit tricky. Can you read this? At the back, can you read what's written over here? No. Okay, so let me just tell you what. So these are the options for the co-integration test. Basically, it's what kind of deterministic terms do you want to include? Okay, so there are 5 options that they give you. So the first option is that there's no trend in the data. No time trend in the data. Second, there is a linear time trend in the data. Third, there is a quadratic trend in the data. And within each, there are other sub-options as well. Okay, so the one that we're going to use most of the time is the middle option. So So CE is the co-integrating equation. Okay, so the option that we're going to use, that's also the default option, is that there is a linear trend in the data and there is an intercept in the co-integrating equation. Okay. The next option is that there is an intercept and a trend in the co-integrating equation. Okay. So why do we use this most of the time? Well, if we look at most of the macro time series like GDP, etc., they do have a linear trend, a linear time trend. Second, when we look at most economic models, right, they may tell us, for example, money demand depends on GDP. Okay, so money demand could be co-integrated with the real GDP. But it's unlikely that economic theory will say that money demand depends on GDP and a time trend. Okay? Most of the time, economic theory will not give us a time trend in the co-integrating equation. Okay? Most of the time, economic theory will tell us, well, money demand depends on GDP and the interest rate. Okay? So there should be, generally speaking, no need for a time trend. So the default option is linear trend in the data, and then there should be an intercept in the co-integrating equation. So what does that mean? If there is a linear trend in the data, how come there is only an intercept in the co-integrating equation? What is that telling us? There is a linear trend in the data, but not in the co-integrating equation. Where is the trend going? The variables have the same deterministic time trend as well. Okay? So the co-integrating vector, it is cancelling out not only the stochastic trend, but also the deterministic time trend. That's the default case. That's what we call, last time we called it the deterministic co-integration restriction. Okay? So the same co-integrating vector which cancels out the stochastic trend also cancels out the deterministic trend. So you do not need to include a trend separately. Okay? Which specification we should use? So it depends on the data and the underlying economic model that you're trying to test. Okay? You have to use common sense to figure out what is the best option. Okay? Some people will just play around and see which one gives them the best results and simply report that. Not always the fair thing to do, but in practice, researchers will play games with different. Okay, so for us, we can stick to this option. We allow for linear deterministic trend in the data, and then an intercept, but no trend in the co-integrating equation. Okay, but you have other options as well. Most of the time, the default option will be good enough. So let's just click that and see what happens. So in the Johansson procedure, there are two tests. One is what is called the trace test. Okay, so first we are looking here. Now let's try to see what these results mean. So the good thing about the Johansson method is that it allows for multiple cointegration vectors. So here on the left side, we have different possibilities. Hypothesize number of cointegrating equations. None means there is no cointegration, 0. At most 1. Okay, so here we have only two variables, the long-term rate and the short-term rate. So with two variables, we can have at most one cointegration vector. Okay. With three variables, we can have at most two cointegration vectors. So if you had 3, then it would have none, 1, and at most 2. Okay, now, so this is the test statistic, and this is the critical value, the 5% critical value, and this is the p-value. So let's look at this hypothesis. This is the hypothesis that there are 0 cointegration vectors, and we can reject this hypothesis. So we reject the hypothesis the null hypothesis that there are 0 cointegration vectors. That means there is at least one. Okay? So there is at least one, then we move on to the next one. Okay? The next hypothesis is that there is at most one. Can we reject that there is at most one? No, we cannot reject. Okay? So we reject that there is 0, and we do not reject there is at most 1. So that tells us how many vectors are there. Well, there's exactly 1. There is exactly one cointegration vector. So that tells us that there is a unique co-integrating vector. So the Johansson method, there are two tests. One is the trace test. The other is the maximum eigenvalue test. And they both give us the same results. They're both telling us that there is one co-integrating vector over here. So this is the same thing. So here it even gives you the conclusion. The trace test indicates one co-integrating equation at the 5% level. And then eigenvalue test indicates the same, one co-integrating equation at 5% level. Okay, the next thing about the Johansson method, it gives you the normalized co-integrating coefficients. Okay, so this is the normalized co-integration vector. So this is the normalized co-integrating vector, and this minus 1.03, that's the coefficient of the short-term rate. So this is something you have to be very careful in interpreting, okay? The Johansson method is giving you the normalized co-integrating coefficient. If we were to write it in regression form, okay, so just because there is a negative sign here does not mean that there is a negative relationship between the long-term and short-term rates. Okay? Because this is a normalized co-integrating vector. If you write this in regression form, this will actually flip the sign. It will go to the right-hand side. And then it is actually indicating a positive relationship between the short-term rate and the long-term rate. So you have to be careful when you're interpreting. A negative sign here actually means there is a positive relationship between the two variables. Is that clear? Okay, good. So now we have this. Okay. So what have we done so far? We have looked at 3 co-integration tests. 2 of them are single equation. 1 of them is the Johansson, which allows for multiple co-integration vectors. Now, once you test for co-integration and you find that there is co-integration, what should be the next step? So you do the Engel-Granger test, the Phillips-Ulliaris test, or the Johansson test, you find that there is co-integration. The next step is estimating the co-integrating vector and conducting inference. Okay? So in the Johansson test, that is built in. Right? You are testing for co-integration, you're getting the co-integrating vector at the same time. Okay? But for the other 2 tests, you're not getting the co-integration vector and the standard errors. So it turns out that there are other methods of estimating the co-integration vector which are also efficient, okay, asymptotically efficient. And Johansson is also, the Johansson method is also asymptotically efficient, but it makes very strong assumptions about the error term. It assumes that the error term is normally distributed, okay? And that may be a very strong assumption to make, that the error term is normally distributed. So there are other methods for estimating the co-integrating vector, which I'm going to show you now. Okay? So after we test for co-integration, we're going to estimate the co-integrating vector. So you open equation now. Instead of opening group, to test for co-integration, we open the group. And now we are going to estimate the co-integrating vector. So we click open equation. So now you specify your equation. So what are the dependent and independent variables? So long-term interest rate, short-term interest rate, and then we want to have a constant in here. Okay, so that's the equation. And here you choose the estimation method. So the default is least squares. We don't want least squares. We want to estimate a co-integrating regression. So there is an option called coint reg, co-integrating regression. So we choose that option. Okay, and then that opens up this box. The first thing is to specify the dependent and independent variables. Second, the trend specification. Okay, again, in the trend specification, the same thing as before, constant, nothing, constant, linear trend, quadratic trend. So we stick to a constant here. Okay. Any other deterministic regressors, any dummy variables, something, we don't have any of those things. So then you choose the method, okay? Now there are 3 different methods for estimating the co-integrating vector here. You could use any of them. The first one is called fully modified OLS. Okay, so based on OLS, but it modifies that, so we get the correct standard error. Okay, OLS, if there is co-integration, OLS is super consistent, right? But the standard errors that OLS gives us are not correct for hypothesis testing. So fully modified OLS gives us the correct standard errors. So that's one method. So we can use that. So let's just click OK.
他每次来上课都穿西装，我 Frank 每次感觉他穿着拖鞋来了。
Okay, so now you can see that fully modified OLS. Now the coefficient of the short-term rate 0.96. This standard error is the correct standard error, so we can use that for inference, and you can see it is highly significant. P-value is 0. Okay, so how does this compare with Johansson? Okay. Now remember, Johansson gives you the normalized one with this negative thing. When you write it in the regression format, you get a positive value. Okay? But when you're doing fully modified OLS, you're already getting the regression version of the co-integration vector. So this does not need to be changed. The coefficient is 0.96. Okay? So 0.96 here and 1.03 here. So pretty close. What if we try some other options? So you go back to estimate and change the method from fully modified OLS. The next one is dynamic OLS. And you click OK. Dynamic least squares, DOLS, dynamic ordinary least squares. And now coefficient similar to before, 0.986. The last one, go back to estimate, change the method to, the last one is called canonical co-integrating regression, CCR. Canonical co-integrating regression, CCR, coefficient is 0.95. Okay, so you can see that we used 4 different methods of estimating the co-integrating vector, and all of them are giving us values 0.95 to 1.03. Okay, that is the range. So basically close to 1 is your coefficient. Something quite robust. Okay, any question about how to do this? Okay, so this may be a good time to take a break.